All right, looking at the first question that was brought in terms of homework here. Let's take a look at this here. This is the use a calculator to solve the equation, or the equation on the interval 0 to 2 pi, and then there's our equation. So let's go for it here. So first thing we've got to notice is, because it's from 0 to 2 pi, first of all, we are in radian measurement. That's the first thing we should notice. Second thing that we should notice is how many revolutions are we looking at in this case. Because 0 to 2 pi is a single revolution. So with that, I think we're ready to start. So writing down the equation a little bit lower. Let's see, I'm going to add subtract 5 from both sides. It gets me -5 divided by 6, and that gives me tangent theta is equal to -5/6. Now here's a little problem. Because it is a negative, we are going to do a few things here. Alright, so that because of that right there, we've got to think to ourselves here. Around the unit circle, as you do one full revolution around the unit circle, which quadrants is tangent going to be negative in? So I think tangent is going to be negative in quadrant 2, and I'll put a little line up and I'll already make my little triangle there. Also in quadrant 4, I'm going to make a different triangle there. Okay, so what are we trying to do here? We're trying to get the radian angle measurement to see what makes that true. Alright, before we do that though, what we have to do is think of something called a reference angle, which I think you guys worked out already here. A reference angle is an angle that is the triangle, forms the triangle in quadrant 1. So it's a theta with like a little slash sometimes above theta, sometimes a dash above theta, just depending what you want to use it as. And that one is going to give us the triangle that is in quadrant 1. So when we do that here, we're going to set this up, and now we're going to have to use a little calculator most likely. So that's what I'm trying to find. I'm trying to find theta, sometimes called Theta Prime, as the reference angle, or the reference angle of theta. All right, first things first, I gave a little, put up a little thing on the TI-83, kind of just a cutout here, or a little snippet of a TI-83 calculator. Make sure, first of all, you are in radian mode. Make sure you are in radian mode over here, right there. All right, because if you're in degree mode, then you're really in trouble. So what do? You have to go to the mode button on your calculator. Hopefully you guys know what that is. It's next to the let's see, let me find out where it is. Thought I had it here. It's going to be to the right of the second function button. Okay, so with that, make sure we're in mode, and then we're going to calculate. We're going to put in tangent inverse of just a +5/6. Now what that gives us this angle measurement right here. Gives us the reference angle if that angle was in quadrant 1. And then we're going to use this to move it around everywhere else. So if that is the measurement of the angle in radian measurements in quadrant 1, that means the reference angle here in quadrant 2 is going to be exactly the same, but we want that right there. We want the angle measurement that measures up to that reference angle. So hopefully you know this earlier here. If you're in quadrant 2, if you want to go from the reference angle to the real angle, what you want to do is you want to subtract that reference angle from pi. So it's pi minus whatever your reference angle was. And again, do that on the calculator here, and you should get a 2.4. It looks like I need 2 decimal place accuracy, so 4.5. So in quadrant 2, what you do is you subtract, or you take the reference angle, you subtract it from pi. In quadrant 3, what we do is we take pi and we add the reference angle together. In quadrant 4, we subtract it from 4 pi. So notice there's my reference angle. That's the angle that I want. So in quadrant 4, the rule is you're almost at a full revolution. You're almost at 2 pi. And the gap is the reference angle. So we say 2 pi minus that reference angle. So punch it in a calculator here. And you don't want to use 3.14 as approximate for pi because you're not going to get the answer that you want. And since you want 2 decimal place accuracy, you probably want to use actually the pi button on the calculator here. So 2 times pi, subtract 6.6947 will get you a 5.59, I believe. So there it is. There's your 2 answers for this first problem. Moving on to the second problem. This is section 6.5 homework. It is problem number 17 off the homework or thereabouts. All right, this one, oh, look at that. Find all the solutions of the equation in the interval from 0 to 2 pi. Again, just like the previous problem, we understand we are in radian measurement because of the 2 pi and no degree sign visible. And also we're looking at 1 revolution still. So we're looking at 1 revolution to solve this problem. All right, with that said, let's start solving it here. Hey, I noticed that this guy is a cosecant function. Well, my calculator does not have a cosecant function, so let's see what we're going to do about that in just a bit. So first things first, let's solve for the trigonometric function itself. So we want to have cosecant x all by itself. So we subtract 7 from both sides, gets you that, and divide by 6, and that gets you negative 7/6. All right, on the calculator, if you noticed, you don't have a cosecant function button, you have a sine, cosine, and tangent. So we're going to convert this guy into the sine function. How do we do it? We do it because of this little rule right here. The sine function and the cosecant function are reciprocals of each other. So that means if I take reciprocal of the left side of the equation and I take the reciprocal of the right side of the equation, I will get what I want. So cosecant changes into sine of x, and negative 7/6 changes into negative 6/7. All right, there's our negative again. Okay, so let's think about this here. The sine function. When is the sine function negative? I think it's negative in quadrant 2? No, 3. There you go, 3, because it has to be below the x-axis. Then also it is negative in quadrant 4, being below the x-axis. All right, since it's negative, and no matter which way anyways, I'm still going to figure out what is the reference angle. So the reference angle is going to be made by finding out the sine inverse of the positive value. So sine inverse of 6/7, again, have to punch it in on a calculator most likely here, but what we really are trying to find before we punch it in is this place right here. If we were in quadrant 1, punching it in the calculator here, the radian measurement of that angle would be 1.029696801. Now we also have another problem. The other problem is the fact that it wants us to round to 4 decimal places. So I'm thinking to myself, you know, I'm probably going to leave a whole bunch of decimal places, at least 5 decimal places, and then I'm going to round certain numbers at the end. Let's do that. That'll probably be easier. All right, let's go with it here. So that is the reference angle. So x prime, or reference angle of x, is 1.0296968. So we got 1, 2, 3, 4, 5, 6, 7. A little bit of an overkill, but that's fine. All right, so we are now, that's the reference angle right there, but according to ours here, we want to be in quadrant 3. So quadrant 3 is going to be that angle. That's the angle measurement we want right there. So we want to go half a circle, and then we want to go some more. So in quadrant 3, to go from the reference angle to the angle itself, what we do is we take pi and we add it with our reference angle. All right, again, use the pi button on your calculator for more accuracy. So pi plus that big number that we have down there, add it together, and that's going to give you a 4.171, and because we need 4 decimal place accuracy, how about a 3 there? Okay, that's done with that one. Now let's go on to the other one. So in quadrant 4, that's the other time that the sign is negative. What I want is the angle measurement. Here's my reference angle, and the angle measurement that I want is that right there. All right, again, how do you move from reference angle to the angle itself? So we are just shy of 1 revolution, so it'll be 2 pi, subtract the reference angle. Okay, punch those in, see if you can do it ahead of me here. So 2 times the pi button in your calculator minus that number that we got for the reference angle, and I got 5.253 and 5 at the end for 4 decimal place accuracy. There it is. There's my 2 answers, and I am done. All right, moving on to the next problem here. So we're trying to solve sine of a x plus pi over 4 is equal to root 3 over 2. So let's go for it here. All right, here we go. Noticing we are from 0 to 2 pi. Once again, we are in radian measurement. And we have 1 revolution on our hands. That's what we want to do. So initial look at it is 1 revolution. Well, let's write down the problem. All right, notice it's not just sine of x, it's sine of something inside there. So what we do is we're going to take the sine inverse. On the left-hand side, you're still left with x plus pi over 4. So we're going to take the sine inverse of root 3 over 2. Now that is a specific value. We're going to look at all the way around the unit circle. When do we get a sine value of root 3 over 2? Or even better yet, on the unit circle, when do we have the y-coordinate to be root 3 over 2? And you can do it one of 2 ways. You can think about it, or you can go to page 509 in your textbook. It has a unit circle over there. And with that, you can just look at it here. And as you look at it here, you're going to see something like this here. As long as you're looking at the unit circle like this, you're going to see, you know what? I have a y-coordinate right here. That has a y-coordinate of root 3 over 2. All right, then also I have another one right here. It's positive root 3 over 2 on this side as well. Those are my 2 y-coordinates that give me exactly root 3 over 2. So I want to know what this angle is. And then I also, that's going to be pi over 3 if I look at it, the textbook. Yep, And then if I think about it, then I want that one over there. And the second time it hits, and that's going to be 2 pi over 3. So there's my 2 answers. Around the unit circle, there are twice where the y-coordinate hits root 3 over 2. And so I have 2 answers here. Now, what I've just done is I have simplified that whole entire right-hand side of the equation. And I got 2 different answers here. So x plus pi over 4 is equal to a pi over 3. The other answer is that x plus pi over 4 is equal to a 2 pi over 3. So in that point, now you have to finish it off. Now you could multiply by 12, that would do it, or you could just subtract pi over 4 from both sides. Whichever way you want to do it. You can either multiply through by common denominators, solve, or just work it out this way here. Still need common denominators here to finish it off. So I guess I need a 12 anyways here. So 12, that would make 4 pi. 12 down here, let's see, 4 times that make negative 3 pi, and then 4 minus 3 pi makes pi over 12. There it is. On the other side, we're going to subtract pi over 4, cross it out over here on this side, and then do the exact same thing here. Get common denominators here. 12 here, that would make a negative 3 pi. 12 there, that would make 8 pi. Minus 3 pi, and how about a 5 pi over 12 as my 2 answers? There it is. So I figured out when sine inverse of 3 pi over 2 happened, and from there then I had to adjust that pi over 4 each time to get me my x answer. Moving on to the next one here. This is 6.6 homework, and this is the long one. All right, right, first things first, what we notice is we're in degree measure this time. Degree measure. And we are at 1 revolution. Now, you've got to be kind of careful here. We are, yes, at 1 revolution, but notice right here, you're not taking sine of theta, you're taking sine of 3 theta. So the book does it differently. It does this whole abstract answer, and then it gives you concrete examples. I don't like that. Kind of 2 different ways you can sort of think about this. If you're going from 0 to 360, right, that would be 1 revolution. But because you have that 3 theta there, what we're going to do initially, just to get our answers, and then we'll bring it back between 0 and 360 later on. But because of that 3 theta there, what we're going to do is we're going to think about 3 revolutions initially, and then bring it back down to what we want. So 3 revolutions to solve the angle problem. That's what we want to see here. All right, let's go for it here. So 8 sine of 3 theta plus 7 is equal to 0. If I were to subtract 7 from both sides, that's what I get there. Divide by 8 gets me a negative 7/8 on that side here, and we have a little problem on our hands. Again, because that negative there, we're going to think of reference angle, then we're going to think of what to do about it. But first, before we do that here, when is a sine value going to be negative? Which quadrants? Sine is positive in quadrants 1 and 2, and therefore sine is negative in quadrants 3 and 4. So we're going to try to look for angle measurements in those quadrants based upon the reference angle. So here it is. I'm going to just solve for the reference angle. I just need to figure out what angle measurement would make sine to be a value of 7/8. Now remember, you're in degree mode, right? So go back to your mode function, because if you don't change this up, you're going to be in radian modes, but you're going to be trying to solving stuff in degrees, and that's going to mess you up completely here. So go to the mode button next to the second function button, and then scroll down, use the arrow keys to go to degree measurement, and click enter, and now we'll highlight degree measurement, and then from there you can quit or quit out of there, go back to the home screen, and then now let's punch it in. So sine inverse of 7/8 gives you 61.04. Let's see, we want to go round to the nearest tenth, right? So I'm going to round it off already here, so 61.0 degrees. I'll use that right there. You could use 0.4, that's fine. All right, so let's go with it here. Don't have enough space left on the previous slide, so I'm going to go to this next one here. So real quick here, our reference angle that we just learned was 61.0 degrees. And that will be our reference angle, 61.0 degrees here, and 61.0 degrees there. So because I'm in quadrant 3, what I do here is that I have a full half circle, which is 180 degrees, and I'm going to add another 61 degrees to get me to where I need to be. All right, if that happens here, I'm got myself 241. All right, let's go to the other reference angle over here. This is in quadrant 4. And so in this case, what we do is we say it is just shy of 360 degrees. It's 360 degrees, subtract 61 this time. And if we do that, you get 299. There's our angle measurement there. Okay, now let's talk about it. Now this is just based upon 1 revolution, right? This is just solving for theta, but our angle measurement is actually 3 theta. So here's what we want to do. We want to be able to go 3 times around the unit circle, or around the revolutions, and get to the same exact, we call it terminal position. So what we just figured out, that was 241 right here. That's what we just figured out right there. What I want to do is I want to be able to go all the way around one other revolution and still end up with the same spot, something like that right there. It's kind of like a little swirl showing here, but that's what I want. But really, if I go around, isn't that really just a full revolution beyond the 241? So if I think about it here, hold on, that is really just going to be 241 plus one full revolution of 360. So if I add that up, it gets me 601. That's cool there too. All right, and then I'm going to do the same thing over here. If I wanted to get a one full extra revolution, I'm going to add 299 with 360 and gets me 659 degrees. And again, third revolution, because we have 3 theta on our hands. So that's going to be the next one. 601 plus another 360 gets me 961 degrees. And on the other side, 659 plus another 360 gets me 1019 degrees. Again, this is the long problem here. If you got to this problem, you're doing great. All right, what we did is we solved for our reference angle theta, but our problem really has 3 theta inside it. So what we've done is we've found out the answer to 3 theta. So here's what we got. We got 3 theta is equal to 241. We have 3 theta is equal to 299. Notice it's each of those angle measurements that I learned about, but I've solved for 3 theta here. So 3 theta is equal to 601. 3 theta is equal to 659. 3 theta is equal to 961. And 3 theta is equal to 1019. So what I'm going to do here, I still have to solve for theta, right? That being actually not the reference angle, but theta itself. All right, so what we're going to do, this is it right here, just divide by 3. 3 goes into 241, how many times? 80.333 repeating, and the instruction says go to the nearest 10, so there it is, 80.3. Divide over here by 3, therefore we get theta is equal to 99.7 degrees. There it is. All right, divide by 3, divide by 3. And how about a 200.3 degrees? Over here, divide by 3. And how about 219.7 degrees? And the last one here, dividing by that here, so how about theta is equal to 320.3 degrees? And then theta finally is equal to 339.7 degrees. All right. So these guys here, the ones with the check marks, check on that one, that one, that one, that one, and that one. Those are all the answers. There are sort of 6 answers to this problem. All right, and 7.1, the person that was doing this here asked for help here, so I'm doing the homework sections here for this one. So 7.1, the law of sines, that's what this section is all about. All right, and it's given to you, the law of sines right there in that, sorry, it's incorrect dialogue piece there. All right, how do we do the law of sines? Law of sines is the connection between the angle and its opposite side. That's what you want to sort of take away from the law of sines. And so in this case, if you think about it, it connects angle A with little a. It's the connection between the angle and its opposite side. That's that 64 in the bottom, and the B here. It's the connection between 52 degrees and that C value there. All right, so because we already have I guess 2 of the 3 angles of a triangle. If I have 2 of the 3 angles of a triangle, I can add them up and subtract from 180 and get the third one here. So angle A, the measurement for angle A would be 52 plus the 64 gets me 116 degrees. And if I subtract that from 180, which is the sum of all the interior angles of a triangle, I get myself, hey, 64. Okay, that's kind of funny. I do have a 64 angle. Hey, this guy is going to be an isosceles triangle, if you know what that is. Don't need to know that for sure, but good there. So this person got A correct. Angle A is 64 degrees. That's cool. All right, the rest of the stuff here. What do we do? Now, you could write it like this. The there's three things that are being compared, right? A and sine of A compared to B and sine of B compared to C and sine of C. And you could write them upside down. You can put the sine of A on top and little a on the bottom, whichever will work. My preference is like this. And you got to name which angles you're going to work with here. So since I know angle A, I'm going to figure out what little b is all about, because I know the sign for b. I just need to figure out what b is. So I can write it like this. I can write it how's it written in the dialog box. It doesn't matter, it means the same thing. Okay. All right, let's put in what we know here. So sine of 64, which is angle A, we just figured that out, over a little a, which I know, is equal to the sine of 64 over here. That's angle B over little b. Now, you can kind of tell if the top numerator is the same, you know the bottom is going to be the same too. So really, right here, you can actually say, hey, b is equal to 13. Or if you realize that this was an isosceles triangle, you would have got that too. But if you didn't, you just sort of did the calculation to it, that's fine. What you do is cross multiply here. So if you did cross multiply, it would be b sine of 64 is equal to 13 times sine of 64. And if you divide both sides by sine of 64, you know those guys are exactly the same. It's exactly the same piece there. So those cancel and left with b equals 13. That's the easy one. All right, that's just recognizing it's an isosceles triangle. So b is equal to 13. The one that you really use a calculator for and actually finish up is the comparison between, and it doesn't matter, it kind of depends what you want to do. I'm going to compare sine of angle A to the sine of angle C. Now, since you know what little b and angle B is, you could have actually used b as well. So you could have wrote sine of b over little b. So it doesn't really matter which way it goes, as long as you know the side and its opposite angle, you can work with these law of sines. All right, let's go for it here though. What do we know? Sine of A is sine of 64 over 13 equal to sine of 52 degrees divided by C, and that little c is what we're going to try to figure out. All right, let's go. Let's cross multiply here. So to get out of the fractions here, I got C sine of 64 is equal to 13 sine of 52. There it is. There's my cross multiplication. In order to solve for C, I would have to divide by sine of 64. One side, sine of 64 on the other. And this time you can't cross cancel them, or you can't cancel them, sorry, because the degree value is different. I can cancel them on this side, but not on the other side. So now I need a little calculator here. I need to put this in the calculator. I put 13 sine of 52 over sine of 64 into a calculator. Now, real quick here, make sure you are in what mode? You are in degree mode. That will make an important thing there. And with that, let's punch this in. Try it yourself here. Here's what I got. I got 13. Now, if you put numbers and trig functions close to each other, the calculator does know, at least the the TI-83 calculator does know that you have a multiplication on your hands. So 13 sine of 52 divide by sine of 64, and we get ourselves 11.397 to the nearest hundredth, then would be 11.40, and that's in terms of feet. I should put the feet over there to the other side too. So there it is. So B is 13 feet, C is 11.40 feet. All right, and hopefully that helps.